Welcome back, everyone. This is Professor Rood, and this is our 5th video for Chapter 9, Geologic Time. Here we're going to look at some common isotopes used in dating rocks. The first method is potassium-argon. Potassium-argon dating method happens to be very versatile. Potassium-40 has a half-life of 1.3 billion years, and it can date rocks as young as 100,000 years. What happens in potassium-argon radioactive decay is potassium-40 will decay to argon-40 and calcium-40. Now, the calcium-40 is not useful, but the argon-40 is. So argon-40 is only present in rocks as the daughter product of potassium-40 decay. Here are a list of some other pairs of isotopes that are frequently used. Uranium-238 decays to the stable daughter product, lead-206, half-life 4.5 billion years old. We have uranium-235, thorium-232, and rubidium-87, strontium-87, 47 billion year half-life. And here's our potassium-40, argon-40 I just talked about. So these are some of the more common isotopes used for dating rocks. In determining the ages of rocks, we have to look at the ratio of parent to daughter isotopes that are left in the sample. This is a complex process, as some radioactive materials do not decay directly to stable daughter products. Instead, they go through many steps of unstable daughter products until stability is reached. A good example is uranium-238, which requires 14 decays before getting to lead-206, which is the stable daughter product. There are, of course, sources of error in radiometric age dating. One important concept is that the system must remain closed. That means no new material can be added or taken away. If that happens, for example, if additional uranium were added to a sample that you were dating by a uranium method, this will affect the results. So no external addition or loss of parent or daughter, and a fresh unweathered sample is most important. The oldest rocks that are found on the continents have been found to be older than 3.5 billion years. So this confirms the idea that geologic time is quite immense. I want to mention another dating method, and it's dating using carbon-14. This is useful to archaeologists, anthropologists, and geologists who study recent events. Radiocarbon dating uses carbon-14 to date geologic recent events, and its half-life is 5,730 years. Because of a relatively short half-life, the useful range for carbon-14 is up to about 70,000 years. If you have something that is older than 70,000 years, carbon-14 cannot be used. Carbon-14 is not occurring naturally on our planet. It is produced in the upper atmosphere by cosmic ray bombardment. Once carbon-14 is produced in the upper atmosphere, it gets incorporated into carbon dioxide, brought down to the earth by rain, and gets absorbed in everything. So we all have carbon-14 in us. Here's an image. Nitrogen is the main gas in our atmosphere, as shown here. And neutron bombardment, actually, cosmic bombardment will release neutrons, which may then go and hit a nitrogen-14 atom and cause a proton to be emitted. That is the process of producing the carbon-14. Carbon-14 stays in your system at a relatively stable level until an organism dies. At that point, the carbon-14 decays back to nitrogen-14, as shown in this diagram. So here we have the carbon-14 changing back into nitrogen-14, and this is a beta decay process. So a beta particle is emitted. This picture is showing a drawing on a cave wall dated at 35,000 years old, and it was dated using radiocarbon technique. The geologic timescale was developed over many years. Initially, just the names of different eons, eras, and periods and epochs were placed on the scale. Once radioactivity was discovered, numerical ages were then put on. Let's take a look at the geologic timescale. We can see that the largest amount of time is the eon. So we currently live in the Phanerozoic eon. Other eons include Proterozoic as well as Archean. Collectively, the Archean, Proterozoic, and we can't forget the Hadean here, are known as the Precambrian. That is the time before the Cambrian period here. So eons are subdivided into smaller units called eras, listed here. Eras divided into periods, and periods into even smaller units of time, epochs. So these names were originally put on this time scale, and then after radioactive isotopes were discovered, the ages of these time units were applied. With the eon, the greatest expanse of time, the Phanerozoic eon is the most recent eon, and in fact what we live in. If you remember back in the igneous rock chapter, phaneritic texture, phaner meant visible. Well, Phanerozoic, phaner means visible, zo is life. And then the three eons are the eons are divided into eras, and the three eras are the Paleozoic, Mesozoic, and Cenozoic, which Paleo is ancient, Meso means middle, and Ceno means recent. So the eras then can be divided into periods, and periods into epochs. The Precambrian eon is the most expansive. It represents 88% of Earth history. We know far less about the Precambrian just because of the age of that time period, the lack of fossils, the early beginnings of Earth. As mentioned, the lack of fossils was a problem for the Precambrian and in understanding it. We did have life back then, but they were simple forms that lacked hard parts. So we had algae, bacteria, worms, fungi. It wasn't until the beginning of the Cambrian period, 542 million years ago, that the organisms had evolved to the point where they had skeletons and/or shells. Many of the Precambrian rocks are so old that they have been highly deformed. They have been metamorphosed, and that destroys, oftentimes, the fossil evidence. The Hadean refers to the earliest interval of Earth history before the oldest known rocks. A new term has recently come about called the Anthropocene, and scientists are suggesting that this is the time since the 1800s where Earth has seen changes to its climate due to the industrialization. Igneous rocks are the best rocks for radiometric age dating. However, we also need to determine the ages of sedimentary rocks, which rarely can be dated by radiometric means. How we do this is we rely on igneous rocks, and we will bracket the ages of the sedimentary rocks using igneous rocks. Here is an example. We have sedimentary rocks, Somerville and Morrison. We have a volcanic ash bed that has been radiometrically age dated at 160 million years. And then we have more sedimentary rocks on top of that, the Dakota sandstone, this other layer, shales, all the way up. And then we have another igneous intrusion here, a dike, dated at 66 million years ago. And the best that we can say about these Morrison and the Somerville formations is that they are older than 160 million years old. With the Dakota sandstone, Manco shell, and Mesa Verde, with this igneous dike cutting through and this volcanic ash bed, we can bracket these sedimentary layers and say that they are between the ages of 66 million and 160 million years old. And sometimes that is simply the best that we can do when dealing with sedimentary rocks. This ends our video for Chapter 9. This is the concluding video, and have a good day. We'll see you for Chapter 10.